Hello all, I'm Veeru from electronicsinnovation.com. I'm your host for this episode. In this video, we will look into how to develop ABP activation-based LoRa End Node with STM32 and RFM95 modules. The STM32 is the family of 32-bit microcontrollers based on ARM Cortex-M architecture. It is designed to offer new degrees of freedom to microcontroller users. It offers products combining very high performance, real-time capabilities, digital signal processing, low power operation and connectivity while maintaining full integration and ease of development. That's why I choose this microcontroller to make this project with RFM95 module. Let's see how we can do that. Here is the circuit diagram to interface RFM95 module with STM32 microcontroller. RFM95 communicates with the STM32 via SPI port. I made these solid connections by following the circuit diagram shown in the previous slide. Now let's place the modules in their respective places. STM32 sits in its position. Now RFM95 sits in its desired position. As you can see here, I have added few extra pins here. Why? Because this STM32 doesn't come with a pre-installed bootloader. Without that, we cannot program STM32 with a USB cable. We can say micro USB cable. So we need to use either ST-Link or FTDI module to program the device. As FTDI is already available in my lab, I am going to use that. For that, I have added these pins. Here is the circuit diagram to interface FTDI module with STM32 microcontroller. I have followed the same circuit, soldered the extra pins on the Vera board. After connecting the FTDI module to the STM32, the circuit could be something like this. Now the FTDI module will communicate with the STM32 using A9, A10 pins and will be powered with the 3v3 and ground. Now the hardware for the LoRa End Node is ready. So let's see how we can program it. Before stepping into the programming part, I would like to take a moment and thank PCBs.com for sponsoring this project by sending these PCBs. This RFM95 module is not breadboard friendly. So I have designed an external PCB and ordered it on the PCBs.com. PCBs.com is an online PCB manufacturing enterprise which provides all services you need to make hardware for your IoT or embedded devices. If you have a similar requirement, do check out their website for more details. The link is in the description below. Now quickly open the Things Network server. Log into the console and select the right cluster and open the ThingsTech platform. On the home page, we have two different sections called Applications and Gateways. We have already worked on these two sections in the earlier tutorials. We have set up and registered the LPSAT gateway in one of the previous videos. We have also seen how to develop a single channel gateway from scratch and registered it on the Things Network server in the other video. In another episode, we have added this application on the ThingsTech platform and registered few nodes and tested them here. Now we are going to add one more end node and test it for a demonstration of today's episode. Click on the Add End Device. Go to the Manual section and select the frequency band allowed in your country. Only particular frequencies are allowed in different countries. So select according to your country. Select Mac version 1.0.3. Click on Show Advanced Activation Settings. Make sure activation mode is set to ABP. ABP in the sense activation by personalization. Keep the rest of the settings default. Generate dev EUI, dev address, app session key and network session key. We will use these credentials to configure our end node in the coming minutes. Finally, click on Register and Device. That's it. The device has been created successfully. Visit the GitHub repository using the link provided in the description below. Then download the code as shown here. Once the file is downloaded successfully, extract it. Then open the folder. Here we have got an Arduino script file and two images of the circuit we have used in this project. Get into the program folder and open the .ini file with the Arduino IDE. Here is the code to program our STM32. We will be using the LMIC library for this project. You can install this library from the library manager itself. Go to the following directory and select Manage Libraries. Search for lmic.h. IBM LMIC framework library will appear. Install that. As we are using STM32, we need to install STM32 boards plugin to program it using Arduino IDE. For that, we have to go to the following menu and select Preferences. Make sure you have added the following link in the Additional Boards Manager URL. You can find the link in the description below. Once you have added the following link in the Preferences, go to the following directory and click on Boards Manager. Search for STM32 and install these two options. Coming to the program, we need to make few changes in the following sketch in order to make this code work with our TTN LoRa End Node. We have to add device address, app session key, network session key here. All the credentials can be found on TTN. Go to TTN, copy dev address and paste it here. Make sure the credentials should be in the same format as mentioned already. Don't change them. Then copy the network session key. Click on the view key. Click on this to convert key into the array of hexadecimal number. And make sure it will be in MSB format. Copy and replace here. Repeat the same process for application session key or app session key. If you want, you can change the published message. For testing, I have added this. Also, you can change the transmission interval, let's say 30 seconds. Then make sure the pin configurations are matching as per the circuit diagram. Scroll down and check whether the frequency channels are matching with the frequency band you have selected on the TTN. I am from India, so I have configured the same channel for the 865 to 867 MHz. If you are also from India, you don't have to bother about it. You can use the same configuration. But if you are from other country, you have to change them. You could know the frequency channels allowed in your country by visiting the following page. If you are from Europe, you can use these channels. If you are from US, you can use the following channels. Once the channels are provided with the right info, you are good to go. Now, this code can be uploaded to STM32. Connect the STM32 with the laptop using FTDI as mediator. And put the STM32 in the boot mode by shifting the boot jumper from 0 to 1. Then restart the module by pressing this button. Now come back to the Arduino IDE and select the board generic STM32 F103C series. This particular series is the blue pill. And select the right port according to your machine. Keep the rest of the uploading configurations as shown here. And then hit the uploading button. Once the uploading is done, open the serial monitor. Then shift the boot jumper to the normal position, that is 0, and press the reset button. It will run the newly uploaded code. Then you will see the following text on the serial monitor. That means the program started running. Queued a data packet for transmission, and transmission of the data packet was completed. If the following text appeared on your serial monitor, congratulations, you have successfully made this LoRa End Node with STM32 and RFM95 module. Now open the TTN, go to the gateway application live data. You will see an uplink we have transmitted from the LoRa End Node on TTN. We can also see the spreading factor, signal to noise ratio, RSSI of the received data packet. The data packet contains the message we are sending from the device. Normally it will be in base64 encrypted format, but the data is decrypted and converted into human readable format. This happened because I have already done this decryption process for this application in the previous video. That's why the data is automatically decrypted and converted into the human readable format. If I click on the uplink message, we can see the different parameters here. It contains DAV EUI and DAV address, which is the same as we have programmed. Thus, it is confirmed that we are looking at the same device data. This is the uplink payload content. As you can see here, this is the encrypted format which is based on base 64 encryption technique. And this is the decoded data of the payload. If you would like to know how we can decode the payload from the encrypted data packet, you can watch the video's link attached to the above I button. I have already explained in the previous video, you can refer to that. The uplink messages are being received by the network server seamlessly, and every data packet contains the info we had sent from the LoRa End Node. So that's it for this tutorial. This is how we could develop a LoRa End Node that could be activated in ABP mode with RFM95 module and STM32 to publish hello message. Stay tuned to Electronics Innovation for more interesting projects on LoRaWAN communications. So see you on the next video. Bye bye.